Welcome to ECE 442. I'm glad all are safe and healthy. Okay, you got this. Reminder one more time. Our midterm is next Wednesday, November 19. Closed book, closed notes with one 8x11 formula sheets, both sides, your own paper plus a what? Calculator, and the material will be up to, but not including memories, which means what? Flip-flops, transmission gates, dynamic logic, patch transistor logic, CMOS logic, domino logic, all of these that we discussed are included. You follow me or not? But not the memories. Memories, we will leave it till the end. Now, one more comment before we start. Next week, I'm going to come on Monday. I'm going to come to the class. Physically, I will be in the class. I will ask you, do you have any questions in regard to the midterm? If I hear crickets, which means what? No questions, I will continue with my presentation. New presentation on the memories. Did you get it or not? Mm-hmm. But if you do have questions, I will engage you with what? Discussing the questions that you have. Did you get it or not?
Yes, sir.
If you do not have any questions, I am not going to review the material for you. Did you get it or not?
Yes.
Yes or no?
Yes.
You need to tell me we have questions, then I will what? I will engage you with the discussion on the questions that you might have. Clear? Otherwise, lecture as usual. Clear?
Yeah. Can we use the VTC handout on the second midterm?
VCC?
VTC. There's a handout you gave us for VTC.
What VCC?
VTC, the voltage transfer.
Oh, VTC.
Yes, yes.
Yes, you can. Yeah. What do you need this one for?
It says what the regions and then the
Oh, anyway, plus VTC. Good.
for the pseudo NES.
Clear? Now, one more thing before I start. The midterm. If you improve your grade from the first midterm by at least 20 to 25 points, I will put more weight on the second midterm rather than the first term. So just an example. If the two midterms, 50%, 50%, just an example, I will make it what? 20%, 80%. Is that a big difference? It's a huge difference. But you need to show me improvement. And by improvement, I don't mean going to what? From 30 to 35. That's not an improvement. Did you follow me or not? That's just me being pity on you. Did you get it or not? I want to see the 30 go to what? 60. Then I will put what? A huge amount of weight on the second midterm compared to the first one. You don't improve, it remains the same. Did you get it or not? By the way, if you go down, I'm still going to count it as what? 50-50. Did you get it or not? Mm-hmm. So let's assume in the first midterm you got 80, but in the second midterm you got 20. I am still going to count it as what? 50-50. Because it means what? It means that you what? That you became arrogant, that you became what? Complicit, and you ignore the course. That makes it even what? Worse. Did you get it?
Yes.
Any question before I start?
No.
Any question before I start? Good. Let's continue our discussion. From everybody got this? I need to erase it. Everybody?
Yes.
Okay. Now, let's continue our discussion last time, and we are still, by the way, struggling with the what? With the SRAM. SRAM stands for what? Static Random Access Memory. Static Random Access Memory. This is the what? This is the cell. One more time, one more time, one more time. This is the what? This is the cell. By the way, I forgot. You told me to bring it. Totally forgot. So let's hope next time I do not forget.
You want me to remind you?
Huh?
Do you want me to remind you again?
Yeah. You know, I'm useless. I have to be honest with you. I'm useless. This is the sound. Did you get it? A cell can store how many bits? One. So what do I have? We have array of these cells distributed in a what? In a matrix form. Rows and what? Columns. The rows represent the words. The columns represent the what? The bits. That makes up the word. So for example, one more time, if I have 1 megabit memory, I can what? I can say it as follows. Time 01024, which is what? 2 to the 10 times 2 to the 10. Now, you might tell me, Professor, but 2 to the 10 times 2 to the 10 is a little bit more than 1 million. You follow me or not? Yes? For everything is approximate. It's multiple of, sorry, power of 2. Did you get it or not?
Yeah.
Okay, good. So how many words do we have? We have 1024 words, and each word, how many bits? 1024 bits. Did you get it?
Yeah.
Yes or no?
Yes.
Okay. Now, how do we select the word? We select the word by applying a what? A word address in what is referred to as a what? A raw decoder. You follow me or not? So a raw decoder, what are the inputs to the decoder? Is the addresses of the word? Yes? And what is the output? The output is the word line. Did you get it or not? Initially, all the word lines are what? Pre-charged. Then if I want to select one particular word line, what do I do? All the other word lines, I bring them what? 0, and I keep what? The one that I select. This is called what? A NOR decoder. A NAND decoder is the other way around. Did you get it or not?
Yes.
Yes or no?
Yes.
Good. Same thing with the column decoder. Clear? Okay. Now we looked at the decoder last time. You follow me or not? Yes or no? Now remember, when you select a word line, all the what? All the cells in that line are selected. All the cells on that line are selected. But then when you select the bit line, you are selecting only what? One cell. And one more time, if you select a row column, it's a row column. If you select the column, which means what? You are selecting the bit. All the cells on that column will be what? Selected, but only the one who's what? The row is selected, you will be able to what? Write into or read from. Did you get it or not? Which means what? I need the intersection of a what? Of a row, and what? Column. That constitutes a cell. Did you get it?
Yeah.
Cell is like this. This is a cell. This is the word line. And we do have 2 bit lines. One of them is called what? Bit line. The other one is called what? Bit line bar. Yes? And finally, what do we have? We have the I/O. I/O stands for what? The input and
Output.
output. When is it input? When is it input? When you are what? When you are writing into the memory. When it is output? When you are reading from the memory. Did you get it? No response. Did you get it? And we saw how this one works, the read and the write. How do we size the transistors? By the way, how many transistors do we have? This is the 6T, they call it 6T. Most popular one is 6T. Why do they call it 6T? 1, 2, 3, 4, 5, 6 transistors. 2 of them are what? Access transistors, and the remaining 4 are the what? Are the back-to-back inverter. Did you get it or not? Back-to-back inverter. And again, the access transistor, the Q5 and the Q6 are selected by the word line. You see the word line? Oh. Now, missing in this diagram is a what? Is a capacitor here, capacitor here, capacitor here, capacitor here, and so on. All of these capacitors, by the way, are parasitic. What does parasitic mean? Huh?
You don't like them?
No. That does not mean you don't like them. Why you don't like them? They are parasitic. Does not mean that you don't like them. They are not external. They are not. In other words, you are not going to put what? integrate a capacitor in there. It's what inherent in the process. Did you get it or not? That's not the case for dynamic. Let me jump a little bit. Jump a little bit, 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 a little. This one. 1T, 1T instead of 60. This is ridiculous. Do you agree this is ridiculous? 1T. Do you see this capacitor? CS? That's external. That's not the parasitic. Did you get it or not? That is external. You are going to put it there. You, the designer. Clear? Whereas the other C, you see the other C, which is CB? That's parasitic. Did you get it? Good. We'll get to the dynamic in about, what, 15 minutes. Where are we right now? Okay, this one. Yes? Now, one more thing I need to bring before I show you the sensor amplifier. Do you see this? This one. This one. What is this one? That's a sensor amplifier. When you read or when you write, you are actually not reading the what? The actual stored bit. What are you reading? You are reading some delta B. Delta B is very small, around what? 0.1 to 0.2 volt. Did you get it or not? Why? Because you are trying to conserve the what? The power and the what? And the memory. These are what? By the way, is this a large memory or it's nothing?
No.
This is nothing. Do you follow me or not? It's nothing. Clear? So imagine if we do have a memory with millions of these cells, billions of these cells. We are not going to be able to what? To assign each what? Each time I read or each time I write, I assign what? Full power. It's just, all what I need is a what? A delta. That tells me what is the thing that is stored, a 1 or a what? A 0. The sensor amplifier will take care of the rest. Did you get it or not? Yes or no?
Yes.
Sensor. What is sensor? Device that sends what? Weak signals and generate what? Total signals. Did you get it? Either to 0 or to a 1, which I will show you in just a second. Clear? Notice, by the way, there is a sensor amplifier for every what? For every what? Column. For every column, you have a separate what? Sensor amplifier. So this is not the sensor amplifier for what? For all columns, one sensor amplifier. No, for everyone. Did you get it? Good. Another thing about the sensor amplifier, which is a little bit weird, we will see it in just a second. Sensor amplifier, the inputs and the outputs are the same. What does that mean? What does that mean when I say the input to the amplifier is also the same as the what? Output of the amplifier. Which means what? When you input something to the amplifier, the output will come what? On the same what? On the same port, not on a different port. See, if you do have an amplifier, this is an amplifier. That's the input, that's the output. Did you get it or not? A sensor amplifier, the input and the output is the same port. Do you follow me or not?
Yes.
No response. Yes? When you input, this data goes here. When the output, data comes here. On the same what? On the same line, not a different line, not a different port. Did you get it? Okay, good. So let's understand how the sensor works. We went yesterday, but not yesterday, on Monday. We went to see how we can write, how we can read, how do we size the transistors, and so on and so forth. And remember, by the way, the reading, I don't want it to be what? Destructive. When I read something, I want the content of the memory to remain what? The same. I don't want to destroy it. The write, on the other hand, the whole idea about the write is to what? Is to destroy. By destroy means what? Means ability to change the content. Do you follow me or not? But reading, when you are reading the book, when you are reading a book, you should not change the what? The words in the book. But when you are writing on the book, you are what? You are changing words. You follow me or not? It's very simple. Okay. This is the decoder. We already talked about the decoder. This is the one. This is what we want to discuss today. How can I get it all in one screen? What do I need to do?
You could hit control.
What?
Click control and then use the scroll button on the mouse.
I do what?
Control and use the scroll button on the mouse. The mouse.
I don't know.
The mouse. Yeah, the thing that you're.
I don't know.
Right index finger. It's on
I
it.
don't know. You either come and help me or what? Or okay. Yeah. I wanted to see the circuitry for the sensor amplifier. Yes. Thank you, sir. Thank you. Let's understand first of all the components. Before we understand the operation, let's understand the components. Bitline bar. Clear? No response. Clear? And remember, bitline and bitline bar, there is no inverter between them. These are separate lines. Did you get it or not? Which means what? Is it possible they have the same voltage? Yes, it is. Did you get it or not? These are not inverted. Bitline bar. Clear? I want you to look at the top. Do you see the two transistors on the side? These are the access transistors. In other words, this is M5 and what? M6. Agree so far? Okay. What is inside the cell? The back-to-back inverter, which is what? M1, M2, M3, M4. Did you get it so far? Okay. Skip the second portion. We'll get to the second portion in just a second. I want you to look at this portion. Initially. So, how does the sensor amplifier works? The steps. Step 1. Recharge the bitline to bitline. Bitline and bitline bar to what? BDD over 2 to what? BDD in that region. Clear? Assume in our discussion both are recharged to what? VDD over 2. Where is it? Show me where it is. I want you to see VDD over 2. You follow me or not? This is VDD over 2. This is going to here. This is going to here. Now what do I need? Recharge by setting VB to what? 1. 1 means what? VDD. Did you get it?
Yep.
I want you to tell me on or off? On NMOS. These are NMOSs. All of them are NMOSs. Did you get it? Okay. By the way, actually the entire design is what? NMOS, except for those two, the PMOS and the what? And the PMOS in the cell. Did you get it or not? Okay, good. Help me now. Help me. Is this one on?
Yep.
On?
Yep.
What do I say? This VDD over 2. This one is on. VDD over 2 will come here. So this is VDD over 2, charged. This, by the way, what is being charged? There is a capacitor here, which is called what? CBL. CBL stands for what? Bitline capacitor, which we discussed last time. Did you get it or not? Similarly here, we have what? Bitline bar capacitor. Are they large or small? They are large. Why? Because they get contribution from what? All the cells in a given one, in a given column.
I think it shows them up there.
Could you repeat that again?
Shows them higher up. Oh, it does.
Yeah, it doesn't, by the way, it doesn't matter. This line, here, CV, CV alpha. This is the same line.
Yeah.
So if I put it here or if I put it here, it doesn't matter. But I admit, at the beginning, I didn't see them. So that's why I'm telling you it's here. I did not see them. It's already there. Did you get it? No response. Okay. Can you tell me what is the purpose of this transistor?
Make sure they're the same.
This transistor is to make sure that they are what? The two lines are what? Are exactly at what? VDD over 2. Why? Why is this one important? One of these lines will go a little bit what? Up. The other one will go a little bit what? Down. I need to make sure that when they are starting what?
Same.
At the same level. So one of them go up, the other one go down. But if they are not starting at the same level, I don't know who is which is which. Did you get it or not? So this transistor, they call it what? Equalization. Equalization means what? Making sure that this one and this one are what? Are at the same voltage. Clear so far? Now I want you to look at the second diagram. The second box, this box. Phi S, do you see the Phi S? Yes? 0. Which means what? This one is off and the top one is off. Are you following me or not? Can you tell me what remains? What remains is a back-to-back inverter. Yes? Yes?
Yeah.
No response. Yes? This back-to-back inverter, by the way, has nothing to do with the back-to-back inverter of the cell. Did you get it or not? You lost me here. Did you lose me?
Yes, I did.
This has something similar to it here, but they are different. In other words, they are different blocks. Did you get it? Initial. Before you sense anything, initial. What is this? At what voltage? VDD over 2. At what voltage? VDD over 2. Let's stop here for just a second. How could that be? One of them is VQ, the other one is VQ bar. Did you follow me or not?
Yeah.
Initially, they are both at VDD over 2. Where is the operating point? Remember, in a back-to-back inverter, we have 3 operating points. 2 of them are stable, and the third one is metastable. Yes? Did you forget it? Where are we initially? We are at the metastable, which is what? VQ and VQ bar are both what? VDD over 2. What do they need? They need what? A push on one of them to go a little bit more than what? VDD over 2 to start the positive what? Feedback. Remember the amplifier in the meta state, high or low? The amplification, the gain, is it high or low? At the metastable, high. Did you follow me on that? All what they need is a small change on one of the lines to start the what? The positive feedback to go where? Either to state A or to state what? C, leaving state B in the middle. Did you get it? Yes or no?
Yes.
One more time. Which states are stable? A and C. What is the gain at those states? What is the gain? Did you get it or not? Which means what? Once you reach those states, you are not going to what? You are not going to change them unless you exert an external force. Did you get it or not? The meta state, which is the one in the middle, is what? Shaky. Do you follow me or not? Both of them are what? VDD over 2. Shaky. Do you follow me or not? Just a small what? A small force into one of these two lines will cause the what? Will cause the positive feedback to what? To start working. Did you get it or not? Why? Because that small change will be amplified by a large gain at the metastable state. Did you get it? This is yours? This is yours?
No.
Yours? Roar of the Bengals. Okay. It scared me. Are you following me?
Yes.
Everyone?
Yes.
So initially, one more time. Initially, this and this are both at what? BDD over 2. And where are we? Remember? Remember this? Yes? Where are we? Here. This is a stable state. This is the other stable state. We are in the middle. Did you get it?
Yes.
Good. Now, let's continue. Did you understand step 1? So we pre-charge this into what? Into BDD over 2. Each line. Yes? Number step 2. Select the word line. Select the word line. Which word line? The one on the top. Select the word line. Yes? Now, let's go back to the diagram. This one. Now, this one is the cell. This one is this. Oh, where is the voltage? Oh, sorry. Oh, where is the voltage here? VDD over what? 2. Recharge. Where is the voltage here? VDD over 2. You follow me on it? And I'm selecting what? This one. Yes?
Yeah.
Now let's assume what is being stored is a what? Is a 1. Are you following me or not? What does that mean? This is VDD. This is what? 0. You agree?
Yeah.
Now, what are you putting here? VDD over 2. Which means what? This capacitor here will lose some its charge to where? To this capacitor. Which means this one will go a little bit higher than what? VDD over 2. VDD over 2 plus some what? Delta. Did you get it or not? Okay. What will happen on this side? What was this? 0. What was this? VDD over 2. What will happen? Current will go this way. This will lose a little bit. Did you get it or not? So instead of VDD over 2, it becomes what? VDD over 2 minus some delta. Did you get it?
Yeah.
Yes or no?
Yes.
Then what do I do? After I select the word line, after a short period of time, which I'll show you in just a second, select step 3. Select the sensor line, i.e. set phi, what is it? I cannot read it. What is it?
P.
One second. What is this?
PS.
PS. Set PS equal to what? 1. Are you following me so far?
Yes.
What can you tell me about this transistor? On. What can you tell me about this transistor? On. Yes or no?
Yes.
Now, what is the voltage here? VDD over 2 plus what? Delta. What is the voltage? By the way, this voltage is a VQ. Yes? What is the voltage here? VDD over 2 minus delta. Yes? Delta is around what? 0.1, 0.2 volt, very little. Yes? What happened here? What happened here? The feedback, positive feedback, start to what? start, the meta state will go where? The meta state will go either to what? 1, if the delta is what? Positive, or it will go to what? 0, if the delta is what? Negative. Did you get it or not? So at the end of the sensing, can you tell me what is the voltage here? 1, which is what? BDD. What is the voltage here? 0, which means it is exactly what is being what? Stored in this. Did you get it or not? Yes or no? Answer me the following question. Where is the input and the output of the sensor amplifier? It's the same. This is the same. This is the input. This is the output. Here, this is the input. This is the output. Did you get it or not? No response. Yes or no? Yes. Okay, good. Now I want to show you the diagram so that you understand what I'm talking about. Question? Question? Okay. I want you to see the diagram and tell me if you follow me. At the beginning. What is this? X0. What is the bitline? Both of them. Bitline and bitline bar. Both of them are what? VDD over 2. At this point, what did I activate? The word line. Yes? What do you see? Right away. The bitline either go up or go what? Down. Until it get what? Stabilize equilibrium. At this point, what did I activate? I activate the sensor clock. What does he sense here? Positive. What does he take it to? BDD. In here, what is he sensing? Negative. He takes it to what? C. Did you get it? Did you get it? So when he reads, when the sensor sends the what? The whatever you are reading from the cell, he only needs what? Delta. He does not need to what? To have BDD total. He just needs a what? A small infinitesimal small variation for it to what? To start what? The positive feedback. Did you get it or not? Again, one more time. What is the gain? At the meta state. Can you show it to me? High or low? Why? Can you show it to me in the diagram? What? Do you see this one? The slope? It's high. Did you get it or not?
Yeah.
Once it reaches here, what is the slope? 0. Did you follow me or not?
Yeah.
Same thing with here. Once you reach the stable state, there's no more amplification, which means what? It's not going to what? Change. But if you are at meta state, all what you need is what? Yeah.
Is delta E always bitline minus bitline bar?
How do you define it?
Okay.
How do you define it? Now they define it as what? Bitline minus bitline bar.
Okay.
Do you follow me or not? You follow me or not? Now, if it is the other way around, bitline bar minus bitline, then what does it mean? It means when it is positive, it means what? What is being stored is a what? By the way, what is the example that we took? Example we took is that what is being stored is a what? Is a 1. Could be what is stored is a 0. Possible or not possible? How will it change? Tell me how will it change? Again. Okay, so here, initially, what is it? BDD over 2. Yes? BDD over 2. Yes? What is this initial? 0. What is being stored is 0. What happens on this side? Can you tell me what happened? This will go down. Yes? Which means what? This is going to be reduced a little bit less than BDD over 2. Yes? How about this one? Initially, 1 BDD. BDD over 2. This one will increase a little. Did you get it or not? So if you are taking bitline bar minus bitline, If the difference is positive, then what is being stored is a 0. Depends on how you define. Doesn't matter. Remember, by the way, you are starting with the concept that they are both what? Equal at VDD over 2. That's what we did that's why we did the what? The equalization. Clear? One goes up a little bit, the other one goes down a little bit. Yes? The sensor amplifier will catch the what? The delta, and will force the what? Will force this one to what? To operate. Say something. Did you get it?
Yes.
That's how the sensor works. Now, in the DRAM, which we'll talk about next, we have only bit line. We don't have bit line bar. But we still need a what? A sensor. Did you get it or not? We need to see how we can do it with one bit line. This one has what? Bit line bar. The DRAM has only one bit line, which I'll show you in just a second. But before we get into this, I need to make it clear to you that the sensor amplifier for the DRAM is crucial for the operation. Do you understand what that means, crucial for the operation? Which means what? Without a sensor amplifier, a DRAM is not going to work, which I'll show you in a minute. In the SRAM, this sensor is not crucial. It is improving the performance of what? Of your what? Of your RAM, of your memory. Did you get it or not? By what? By only reading what? Small voltages. But if you insist, in other words, suppose I say, I insist to read the whole voltage. Do I need a sensor amplifier? I don't need a sensor amplifier. So I need you to understand that big difference. In the SRAM, the sensor amplifier is a luxury. What is luxury? Is that the right word? Luxury means what? It means you can't do without it. But if you use it, it will improve the performance of your memory. Did you get it or not? For the DRAM, no, it's not a luxury. It is a what? Necessity. We will say why in just a second. Clear so far?
Yes.
No response. Clear?
Clear. So in SRAM, it's possible to read directly from the
You read directly from the cell as a what? As a BDD or what? Zero.
Yeah.
Did you get it or not? This one tells you what? You don't need to spend that much power to read. You can what? Read it with very little what? Very little voltage, and the sensor will take it off. Did you get it or not? That's the luxury we are talking about. Clear? Good. Now, let's get to the DRAM. DRAM, by the way, it started with a 3T, which I will show you after I discuss this. They started a DRAM using what? 3 transistors. They were very happy. Why they were very happy? The SRAM needed what? 6. 3 is an improvement. You agree? Then comes somebody with Intel. He told them what? I can do it in 1. It's like name that tune. I let you listen to a tune. You tell me what I can name it in what? In 1 note or 2 notes. They were competing. Notes, by the way. You cannot do better than 1. Why? Where are you going to store the bit? Did you get it or not? Where are you going to store the bit? You need at least 1. This guy said what? That's all what we need. 1. Let's see how it works. This is a cell. What do you notice? Word line, same as SRAM. You follow me? Which means what? Do I need a raw decoder? I need a raw decoder, just like the SRAM. Do you follow me or not? That's the word line. What do you notice? Bit line, how many? Only 1. Only 1. Which means right away, what does that tell you? A sensor amplifier with the same architecture as the what? As the SRAM, it's not going to work here because there is only what? 1 line. Did you get it? We will see what they did to get around this fact. a transistor NMOS activated by the what? Word line. There is a capacitor here, which is the what? CB, yes? And there is an external capacitor, CS. CS capacitor. And what does the S stand for? Storage. Are you following me so far? Yes or no?
Yes.
Let's start with the right first. Right is easy. Let's start with the right, and you right away we will see we do have a problem here. Let's assume I want to write a what? A 1. Yes?
Yes.
First of all, do I care what is being stored? I don't care what is being stored. You follow me or not? Why I don't care? I want to write a 1. If it is storing a 1, no, I'm done. If it is storing a 0, I will change it to what? A 1. Do you agree? Okay. What do I do? So, the right. For example, writing a 1. One more time. One more time. Do I care about what is being stored? No. I want to write a 1. If it is a 1, then it remains a 1. If it is a 0, then it will change to a 1. Did you get it?
Yes.
Good. What do I do? Step 1. Charge bit line to what? BDD. Did you get it?
Yeah.
Yes or no?
Yes.
Oh. Then what? Select the word line. Can you tell me what happens? Can you tell me what happens? Now let's assume, just for the sake of argument, what is being stored is a what? Is a 0. We'll take both cases. Let's assume at the beginning, what is being stored is a 0, and I want to write a what? A 1. Select the word. On or off? On. This one will what? Charge this capacitor? Yes? We have a problem. What is the problem? Can this one charge all the way to BDD? Why? Because the NMOS passes a what? A weak one. Which means what? This point here can charge only to what? BDD minus BTN. And the BTN, by the way, does it have body effect or not body effect? Huh? It has body effect. Why? This one will be the drain. Current will go this way. Did you get it or not? No response. That was the first obstacle, which is what? The cell cannot store BDD. It can only store what? BDD minus what? BTN. They said, what are we going to do about this? One solution is to what? Boost the word line to what? BDD plus VTN. I'm not sure, did you get my point? Did you get my point? You lost me here. What was this line? BDD, yes? This one charged all the way up to what? BDD minus VTN, and then what? Stop charge. What did they do? They boosted. You understand what boosting means? They boosted the word line to what? BDD plus VT, so that what? This one can store up to what? VDD. Lost me? Lost me? This one of the headaches. One of the headaches. But they tolerated it. They say we can boost the what? We can boost the word line. Can you tell me how do they boost the word line? They remember the decoder? The decoder? They increase the what? The power supply, which is BDD, to what? BDD plus what? T. They increase the power supply, which means what? Adding more power. You lost me here? You lost me. I can see it in your faces, weird faces. Can we go back to here? Where is the raw decoder? Raw decoder. How many of you lost me? Nobody wants to admit that they lost me? A lot of you lost me, but you don't want to admit. PMOS passes a strong 1. Oops, passes a strong what? 0. Yes or no?
Yes.
No response. Yes or no? A PMOS passes a strong what? 1. I said and more. A PMOS passes a strong 1. And instead of making this one VDD, yes, increase the power supply here.
Yeah.
Both to what? VDD plus BTN. Yes?
Yes.
Does he pass a strong 1? Yes, he does. Which means what? When this one is a pre-charge, to what? VDD plus BTN. That's a roll. Did you get it?
Yes.
Yes or no?
Yes.
Good. That's all right. By the way, we are finished with the right. Now, I have a question, by the way. What if the being stored is a what? What if the stored is a what? What if the stored being a 1? What happens? Nothing happens. Why? Can you tell me why nothing happens? This one is what? BDD. This one is what? BDD. Will this one be on? Even though it is selected. Even though it is selected. But will there be current passing?
No.
Why? The drain and the source are at the same voltage. Losing me? Losing me?
No.
Then now do you understand what I'm saying? When you are writing something, I don't care what is what. What is being written inside the cell. I don't care. I am writing a 1. If it is a 1, fine. If it is a 0, I'm going to replace it by a 1. You do understand? Writing is supposed to be what? Destructive. You follow me or not? If 0, you are supposed to what? Destroy it and change it to a 1. Clear? Reading. Losing me?
No.
No. Good. Reading. What do I want? I want to read what is in there. Clear? Okay. What do I do? Follow me here. Again, a bit line, I recharge it to what? Let's say BDD over 2. Similar to what? Similar to the ECE. Anywhere between BDD over 2 to what? BDD. Doesn't matter. Okay. Now let's assume in here there is a what? A 1. So current will go which way? This way. Which means what? This one is going to lose what? Charge. This line is going to what? Go up a little bit. Did you get it or not? How about vice versa? How about vice versa? In other words, what is being stored is a what? 0. What will happen? This will, the current will go this way. Are you following me or not? Resulting in what? Resulting in the reduction of this one. Did you get it or not?
Yes.
No response. Yes or no?
Yes.
I will show you the equation just a second. But in the process, what happened?
Destroying.
The reading destroyed the bit. Is it supposed to destroy it? It's not supposed to destroy it. Not sure did you get this point. Did you get this point? Why? How did it destroy it? So let's take an example so that you understand what I'm talking about. First of all, did you understand the operation? That's a read. That's a read operation. I want you to see the difference. First of all, do you understand what does this mean? Where is it? Too long, too high. Even your reminder was not adequate. Why? You reminded me at 11 o'clock at night. Sometime, late at night. So I was asleep, so I did not read it. So anyway, I want to put the blame back to you rather than to blame my memory. Because I would like to think I'm still surviving. Okay, where are these? External? Internal? Why are they connected by this? Because I'm selecting the what? The word one. The NMOS is what? Is acting on. Are you following me or not? Okay. Now, the law of conservation of charge. What does it tell me? The charge can only be what? Distributed rather than what? Destroyed or created. Did you get it or not?
Yeah.
Can only be what? Distributed. So let's see if you can help me. Initially, let's assume what is being stored is VCS. That's the voltage across what? Across the storage capacity. This is either 0 or what? Or 1. Keep that in mind. What is the total initial charge before you select the word line? Before you select the word line, what is the total initial charge? I'm still waiting. CS. What, by the way, what is the relationship between the charge and the capacitor and the voltage? Q equal to what? CB. 240. 240. Of course, you forgot about it. Do you still know what is the units of charge? Coulombs. C, farad, B, voltage. Yes? Mm-hmm. What is this? Verbally. Can you tell me verbally, what is this? This is the initial charge on which capacitor? Storage capacitor. What is this? Initial charge on the bit line. Why it is VDD over 2? Because what? Why I pre-charge the line, bit line to VDD over 2? Yes or no? Yeah. Afterwards, after I select the word line, the two capacitors are in what? Parallel. What is the total capacitance? The sum capacitors in parallel, they add. Yes or no? So what does it become? CB plus CS. What is the total voltage now? VDD over 2 plus some delta. Yes or no? Can you tell me the delta? Is it positive or is it negative? Or does it depend on what is being stored? Depend on what's being stored. If what is being stored is a 1, this one will be positive. Did you get it or not? Why? Because the current will go this way. Did you get it?
Yes.
Okay. If it is negative, what does it mean? Huh? What is being stored is a 0. So, designated by, oops. Delta B. Agree? What is that? Huh? You lost me?
Oh, no.
Did you lose me? No. What is the unknown here? Delta B. Yes? Okay. Keep it on one side of the equation. what do you get? CS, CB plus CS, BCS minus BDD over 2. Do you understand where this came from? No response. Did you understand where this came from?
Yeah.
From this equation. Clear? Since CB is much greater than CS, why? Why CB is much greater than CS? Because CB is a contribution of all the what? Big ones, capacitors. CB is greater than CS. Can I ignore this one? Yes or no?
Yeah.
But can I ignore this one? No, I cannot. You ignore this one, it means you ignore everything. Did you get it or not? You ignore this, which means what? Delta B, CS over CB, BCS minus BDD over 2. Did you get it?
Yeah.
If initially it's a 1, which means what? BDD, this delta will become what? Positive. Did you get it? If initially BCS is 0, what will the delta be?
Negative.
Negative. Did you get it? Okay, so what is this? Delta B, 1. Delta B when the stored is 1. What is this one? BDD minus BDD over 2, CS over CB. Did you get it or not?
Yeah.
Yes or no?
Yes.
One more time. What is this? That's the what? Incremental voltage, which is now what? Added to what? BDD over 2. Did you get it? Oh, good. What is delta B of 0? Delta B of 0 is when the stored voltage is what?
0.
Z. So it's what? Minus CS over CB, VDD over 2. Did you get it?
Yes.
No response. Yes or no?
Yes.
Here comes who? Sensor amplifier. You follow me on that? To sense whether it's what? Positive or whether it's what? Negative. Did you get it? If it is positive, he takes it to what? VDD. If it is negative, he takes it to what? 0. Did you get it? But there is a problem here. What is the problem? The read has destroyed the content of the memory. Did you get it or not? The content of the memory is not the same anymore. Why? Can you tell me why? Initially, let's assume initially is a 1. This one is stored is a what? A 1. At the end of the read cycle, what will it be? 1 minus what? Delta B. Did you get it? VDD minus delta B, which changed. You are not getting this. Are you getting it? Is that good or bad?
Bad.
India. Look at what the sensor will do. When he what? Amplify the what? The variation. In other words, when he get to what? BDD here, BDD, he take the BDD and put it back on the what? On the word line, on the bit line, and he what? Exert the word line again, which means what? He is doing what operation? Right operation. You lost me.
No.
Yes, you did. I can see it. I know you are weird, but you are getting weirder and weirder. Please listen to me. I read a value, which is delta B. Whose I? I'm the sensor. Yes? I read a value, which is delta B. I decide whose I? Sensor amplifier. I decide whether it's a what? Positive or whether it's what? Negative. If it is positive, I will amplify it to what? 1. If it is negative, I will what? take it all the way to 0. Did you get it or not?
Yep.
But the read operation destroyed the content of the memory. Is it supposed to be destroyed?
No.
So what does the sensor amplifier do? Whatever he takes, he put it back on the what? Bit line, and he what? He assert the what? Word line and execute what? Right cycle, which means what? Whatever you read, you are going to what?
Right.
Write it back. To retrieve or to recover what was what? Stored originally.
Okay.
Say something. Huh? All of it, by the way, just to save on the number of cells. 1 piece. Did you get it or not?
Yes.
Before I show you the sensor amplifier, answer me the following question. Do you understand why the sensor amplifier is not a luxury but a necessity?
Yeah.
Because the read operation is destructible. It should not be destructible. Read, you are reading from the memory. You should not change the content of the memory. So without the sensor amplifier, you are not going to be able to read correctly from your memory. Did you get it?
Yeah.
Yes or no?
Yes.
Good. Now, another problem. What is the other problem? It has only one bit line. How are we going to what? How are we measuring differential? We need differential, delta V differential. But this one has only one bit line. What differential with what? Did you get it or not? So what do they do? Ingenuity, ingenuity. This is the mind of ingenuity. Look what they did. They took the what? They took the memory and they divided it into 2 parts. This is, by the way, this is 1/2 the bit line. Remember, by the way, what does the bit line consist of? This is a bit line. Yes? What do you see? Cell here. Cell here. Are you following me so far or not?
Yes.
Yes or no?
Yes.
Another bit line. Cell here. Cell here, and so on and so forth. Yes? Yes?
Yes.
What did they do? They took all the bit lines and they divided the bit line, by the way, are what? These are the what? These are the word line. These are the bit line. You follow me or not? Which means what? This is this. And they divided in half. In half. Which means what? The left and the what? The right. Are you following me so far? Yes or no? Okay. Now, let's take an example so that you understand what I'm talking about. Let's assume I have what? 1,000 cells per bit line. What did I do? I divided 500 cells on the left side, 500 cells on the what? Right side. And then I connected the 2 halves of the bit line, the 2 halves of the bit line to the sensor amplifier, which is the same as the one that is used in what? SRAM. And this is for the equalization and what? Recharging of the bit line to BDD over 2. Are you following me so far?
Yep.
Yes or no? But there is a caveat. What is the caveat? They added 2 extra cells. A dummy cell. This is a dummy cell on the right and a dummy cell on the what? On the left. Did you get it? We will see what is the purpose of this dummy cell in just a second. Are you following me so far?
Yes.
Yes or no?
Yes.
Okay. Let's understand it here. Careful. Notice, by the way, these are the word lines. Remember, you are selecting only one word line at a time. So when you are selecting one, let's assume you selected one word line, it means what? You are selecting this one. You follow me or not? Which means what? All of these, the others, are not going to be what? Activated. Clear? Okay. But I want you to see the dummies. I want you to see the dummies. What is this one? PD This one is what? BD bar. Keep that in mind. Did you get it or not? Okay. Now, what did they do? They pre-charge the dummy capacitor. The dummy capacitor, they pre-charge it to what? BDD over 2. Just like the regular capacitor. This one. Do you see this one? Equalization and pre-charge, similar to this one. Yes? This one. To what? BDD over 2. You follow me so far? Yes or no? Okay. Now, let's assume they want to read this cell. Yes? What do? They activate this line. Yes? This bit line is what? Pre-charge to what? BDD over 2. You follow me on that? What do? Listen to what they do. When they select this one, which is on which side? On the left hand side, they activate the dummy on which side?
The right side.
On the right hand side. You lost me here. Did you lose me?
No.
Yes, you did. Okay, concentrate. Help me, please help me. I want you to see this line. What was it pre-charged with? VDD over 2. What is this one charged to? VDD over 2. I want to select this cell. What do you mean? I need to assert this line. Yes?
Yes.
Which means what? Does this one have any effect?
No.
No. Are you following me so far?
Yes.
Does this one have any effect? No. No. All of them are no. Do you follow me or not? But what do I want? I want to what? Activate this one so that what? So that this line go what? All the way to. Did you get it or not?
Yes.
So this part go what? Down. How about this one? This one is not activated, which means what? The dummy cell is not going to do anything here. Did you get it or not?
Yes.
Yes or no?
Yes.
Okay, what will happen here? This is BDD over 2. This one is activated. This one is going here. Yes?
Yeah.
On this side. On this side. This one is activated. You follow me or not?
Yes.
This one is activated. Remember, this one is charged to what? VDD over 2. Yes? This one is VDD over 2. This is on.
Yep.
Does this one change?
No.
No. So this one remains what?
This is
VDD over 2. Initially, VDD over 2 will change. Depends on what?
capacitor.
What is being stored here. If what is being stored is a 0, what is this line will do? Will go down? No? If it what? If what is stored is a 1, this one will go what? Up? Will this one matter?
No.
No. Why? Disable. How about this one?
No.
No. So this is either going what? Up or what?
Down.
Yes? Yes?
Yeah.
How about this side? This side, no change. Why? This one was a pre-charge to what? VDD over 2. What is this one? VDD over 2. On, but not conducting. Why? Why not conducting? Because the voltage on both sides is what?
The same.
VDD over 2. Yes? Yes?
Yes.
Any contribution from here?
No.
Why? They have not been selected. You select the word line. The word line selected is this one. These are not connected to the word line. Was right? Okay. Let's think. Suppose I want to select this one. Can you tell me what do I do? I want to select this one. Which dummy do I need to activate?
The left.
I need to activate the dummy on the what?
The left.
On the left hand side. Why? Why? So that I get the potential. One more time. Suppose I want to activate this one. This one is on. Yes?
Yes.
Pre-charge to what? VDD over 2. Are you following me so far?
Yeah.
It either go what? Up or it go what?
Down.
Depending on what? What is being stored in the capacitor. Agree? All the other capacitors on, sorry, all the other transistors on this side, they are off. Why? You did not select that. Agree? Now let's look at this one. Don't look at the dummy yet. By the way, is the dummy on? Here. No, dummy is not on. Did you get it or not?
Yes.
Why? This one is, help me, is 1. Which means what? VD bar is what?
0.
It's NMOS. Agree?
Yeah.
All of these, no contribution. Yes? On. What does it mean? This pre-charge to what? VDD over 2. VDD over 2. Anything happens,
No.
remain at VDD over 2. So this remain at VDD over 2. This one either what? Above VDD over 2 or what? Below VDD over 2, based on what is being stored on the storage capacitor. Yes? The sensor will what? Will pick up the voltage difference. Say something. That's what people in the hardware business work on. Trying to what? Improve what? Improve the cost, improve the performance, and so and so. But there is a lot of problem here. But one of the problems that we did not even talk about is the leakage. That voltage across the capacitor is not going to stay forever. It needs what? Refreshment. It needs what? Soft drink. It needs water. Did you follow me or not? You need to what? Refresh it periodically. Otherwise, it will not going to remain the same. Clear? All for what? Using only one cell instead of what? 6. Did you get it or not? People were very excited about it at the beginning. But then what? The euphoria, is that the right word? The euphoria died down a little bit when they say the troubles with it. Saving is okay, it's fine, but then you have what? Other headaches that you have to worry about.
Since the voltage across the dummy cells
Are the same, because we are using equalizer.
yeah, they're always going to be the same. So why do we need to store it on a capacitor?
Why don't we need what?
Why do we need capacitors to store it? Why can't we just always have those at VDD over 2?
This one is on. This one is the same. This one and this one is video, but this one and this one, they are not connected with the rest of the
Yes,
cell.
right. Yeah, I know, but why do we need the capacitors at the bottom of the dummy cells if they're always just going to be VDD over 2 as a
Where
reference?
is the capacitor below the dummy cell?
Like the blue box, the dummy cell?
This
The
one?
CD yeah.
This one is parasitic. This is not extra.
Oh, okay, gotcha.
This the only extra is this one. These are the extras.
Gotcha.
This is already there.
Okay.
Say something. Did you understand it?
Yeah.
How about the equation? Did you understand the equation? Okay. Now I want, let me show you the 3T. 3T came before this one. Did you follow me or not? The irony, 3T does not destroy the reed. Which means what? Does not require what? Refreshment. But it's 3T. They were not excited about it. They say, what? We would like 1T. By the way, there is also 2T. But 2T proved to be terrible. But 1T, 3T was used. Let's see the 3T. Question, do you understand why they call it dynamic? Do you see BDD in the diagram? Do you see a path, in other words, from here, the output, when you are reading? Do you see BDD, the power supply?
No.
No, the voltage is what? The voltage being stored is a what? Is whatever is stored on a capacitor. Did you get it or not? There's no path to what? To BDD or to the what? To the ground. Just sitting there. Clear? Oh. of time. I cannot explain this one to you in 1 minute. I cannot. I will show it to you next time. I just want to bring one point. Could you sit down until I finish, then you can what?
Stretching.
Huh?
Stretching.
Do you understand that there is no connection here? Do I need to put like an arc, or do you get it? This is the read line, this is the word line. They are not intersecting. In other words, this is like this. Did you get it? No, it's fine. Did you get it?
Yes.
Okay, but I ran out of time. Next time I'll explain to you. How many transistors? Okay, by the way, where is the capacitor? 1 second. I didn't show you. That's the capacitor. But I will show it to you next time. Sorry about that. I was hoping to finish this one today. Did not do it. Why? Because I keep what? Repeating ad nauseum until you get it. But what can I do? That's my nature.